the second one, which is introduction to the problem of learning. So there are spaces. What does that mean? There is an input space and there is an output space. Input space is all of your features and data and everything that you can think of which an algorithm will take as an input. And output space is the labels or the real values, something like that. Now, what is a loss function? A loss function is a function which takes two inputs. Both of them are from the output space and returns a real value. So what a loss function is, let's say, the cost of predicting y hat instead of y. So our algorithm predicted y hat, but the real one was the real actual truth was y. So how much error did I make by doing that? When there is a binary classification, 0 or 1, it's simply 0 if y hat and y are same, and 1 if y hat and y are different. You know, either you are right or you're wrong. If you're right, your loss is 0. If you're wrong, your loss is 1. Simple. What about regression? Now, because regression is a real valued, task, like y is a subset of the reals, the loss function is defined as the absolute difference squared. It's just to make it like that's how they define it. It's called it the square loss. Right? So there can be different loss functions for different kind of different loss function for different tasks. And you can see how loss function, choice of loss function is really critical in trying to evaluate or trying to train or trying to do any kind of machine learning. Because machine learning is not something which is really, magic. It's just an algorithm which is trying to minimize the loss, basically. So the choice of the loss can make or break your task, who knows. So the hypothesis set, what does that mean? The hypothesis set is a function which goes from x. This notation means that it is a function going from x to y. This is the collection of all functions which goes from x to y. So which goes from the input space to the output space. This notation means all functions which goes from the superscript to the base. So all functions going from the space x to the space y. So our hypothesis set is a subset of such functions. So out of which the learning algorithm selects one hypothesis, and that hypothesis is a function which goes from x to y, and then we can evaluate the loss on that hypothesis. So how the algorithm chooses, it will depend on the features, it depends on the prior knowledge about task, it depends on all of this. This is another critical tasks that one needs to do. This is just mathematically formalizing what hypothesis set means. So the supervised learning setup is you have training data which are labeled. So a sample S of size small m, drawn IID. This is important. All of these samples are independent and from the same distribution, identically distributed. From X, so they are a tuple. They are a tuple of X cross Y in a distribution D. So this is a sample. It has X1, which is the image with all the features, with all million features and whatever. And Y1 is its label. So the problem then is to find an hypothesis with small generalization error. So you have this labeled sample and you're going to throw it into the algorithm, and the algorithm will give an hypothesis small h, which belongs to the capital H, with small generalization error. Now, what does generalization error mean? The deterministic case, we'll talk about it. The deterministic case would be, let's say the output label is the deterministic function of the input, which is the y, which is the label, is just an f of x. Like there is some f, we do not know, but it is a deterministic f. And our goal is to find that f, just period, find that f. The stochastic case would be that output is a probabilistic function of the input. Like it is not a deterministic function, but a probabilistic one. In which case we want to find some h which makes the least errors. So what's the generalization error? Now this is where we get interest. This is where it gets interesting. So for a hypothesis, fix one hypothesis, it is defined as R. Why it's capital R is because it was also called risk. So I may call this as risk 2. The risk of the hypothesis H is if I draw x and y from the distribution, just 1 point. If I draw 1 point randomly, x comma y from the distribution, so a sample and its label, and then I evaluate our hypothesis on that sample and compare it to the label according to that loss function. Do you understand what's going on? I sample x and y. I got this tuple. I separate the x's and the y's. I put the x in the hypotheses that we have selected, calculate its output that this is y hat, and compare it to y with the loss function. And what is that value in expectation? That is the generalization error. So expected expectation over the entire distribution of x comma y, the loss of h of x and y. That is the risk. It is, you cannot really calculate it because you never know this capital D distribution. Like this is a very abstract concept because you never know this capital D, and you cannot sample indefinitely. Like if it is if it's on a large space, you need to do this. You need to know the actual distribution, and if you know the actual distribution, you don't really need to have h. Like this is really an abstract concept if you think about it, because you need to find the true expectation over the entire distribution, which you do not know. However, empirical error is something that you can know. You have an hypothesis returned by the algorithm, whatever. You have a sample S, it was given to you. Now this empirical error is risk, like R hat, the empirical error is risk. Empirical, it is the average of the losses of all the training samples. Okay, like you give the training sample, you find the hypothesis, and then you test again on the training sample. I get it. It's not that great of a error estimate, because what you are using to calculate the empirical error is the same that you used to train it. Sure, but we still define it this way. You take the xi, which was given to you, you take the hypothesis, put it in there, it returns some yi hat, let's say, and you compare it to yi, and you see the loss, and then you take the average of them. So if you had, let's say, a lot of samples, like infinitely many samples, I don't know, I shouldn't say that, but if you have a lot of samples, you can convince yourself that risk hat is something which can be used to estimate the risk, because the law of large number says that if you keep sampling, you will actually converge to the actual mean. If you can see that the expectation of the empirical error is exactly this, because if you take the expectation over here, from the linearity of expectation, all of these m summands will be separated, and if I take the expectation over xi, yi distributed from this distribution D, all of them are actually the true generalization error, and there are m of them, so the 1 over m and the m cancels or whatever. So expectation of the risk hat is the same as R of h. So what is the Bayes error? The Bayes error is something that we defined, which is the best possible generalization error that an hypothesis can give. In a deterministic case, when the hypothesis is an actual deterministic function, R star is 0. But in a stochastic case, R star may not be 0, but it's fine, whatever. So in binary classification, if there is noise, you can see that the expectation of the noise is the R star. Anyway, we'll move forward on this, which is fine. So another key concept now is learning versus just fitting. If you see in the left hand side, I can be really right. I can be like absolutely 100. I can achieve 100% accuracy if I try to fit something so jagged and complex to this data. But is it good though? Is it a good thing that we want to do? Like, is it something good that we want to do? Instead of doing that, we try to fit a very simple curve, just this little simple curve. It has more errors than this one. This right hand side picture has more errors than the left hand side one. But it's simpler. It's much more simpler. So we need to define some sort of simplicity or complexity. How do we define complexity? That's a good question. And we will. That's the key. We will. So the best hypothesis on the sample may not be the best overall. This is illustrated by this picture, This jagged crisscross function is the best hypothesis on this sample. But it's trying to do something which may not be too good of a generalizer. Generalization is not memorization, That's what we are trying to do. We are not trying to memorize the data. We are trying to learn what's the inherent qualities of the data. So if there is complex rules, they can be poor predictors, like the jagged line we saw. So there is a trade-off: complexity of hypothesis set versus sample size. We'll think about this. There is a trade-off, between complexity and how much data you need, etc. So this is a general, what is the risk of H versus R star? R star is the best possible one. So the H star is the best in class. So what we have here is, let's say we add and subtract the R of H star. So something that I should have mentioned before, R star is the infimum over the entire possible thing, as long as the entire possible thing. But this capital H may not be that entire possible thing. So what we're trying to understand now is, if I return an H from this smaller subset, how does it compare to the best possible error, absolute best possible error? Let's try to introduce another hypothesis class, H star, which is the best in this class. Basically, it is not R star, but it is the best in this smaller H. So we add and subtract whatever, and risk of H minus risk of H star is the estimation error, and risk of H star minus the best in class is the approximation error. You can think of this as like the bias variance trade-off. This term is the bias. How good is it compared to the absolute best in class? The absolute best in class compared to the zero. Let's put R star 0, because for a deterministic case R star is 0 anyway, right? So this is the best in class. How much is the risk of the best in class? If it's high, that means my thing is biased towards whatever this is. And then this estimation is how much my chosen hypothesis varies from the best in class, which is like the variance. You can think of that as the variance. So this, I think, has some sort of bias variance flavors to it. So the approximation is not a random variable. It only depends on the hypothesis class. Again, it's a bias. The estimation term is something that we can hope to bound, because it's the, and that depends on how we choose the capital H. So if we select the capital H set, find the hypothesis that minimizes the empirical error. That's the only thing that we can actually calculate, the empirical error given the samples and whatever. And we try to find the hypothesis which finds the best empirical risk, and that is empirical risk minimization. But H may be too complex and the sample size may not be large enough. So this problem is really hard to do. Like, empirical risk minimization is a hard thing to do. So So let's say that we want to bound we want to find yes, what we're trying to bound here, okay, is, I give you an hypothesis. H. I calculate its true risk and I calculate its empirical risk. I calculate how much they differ. Okay? How much this let's say some oracle does that to me, because I cannot really calculate the true risk, right? Let's say some angel or some sort of a higher power gives this value to me. It will be a one value. It will be a real number. So how much does its true risk deviate from its empirical risk? And now what I want to do is find such an hypothesis for which this is the maximum. Like, every other hypothesis has less than this particular. Every single hypothesis deviation from its empirical risk is less than a particular number. And what that number, I chose it to be epsilon. So what is the probability? The probability that I chose the probability of having the highest possible approximation error. What is this? Now, highest possible generalization gap be greater than epsilon. What is this? If I can upper bound this, that means I can say that with with probability less than that upper bound, every hypothesis will have its true risk close to its empirical risk. Is that because I'm thinking of epsilon as a really small number? Let's say 0.0001. So the true risk is really close to the empirical risk. And I want to bound the probability that this quantity, the true risk versus the empirical risk, goes higher than 0.0001. If I can bound that probability by, let's say, a small number, what I can say that with a very high probability, the true risk and the empirical risks are close to each other. That's the essential idea, you know. So the bound on estimation error for hypothesis H0 given by, let's say I give my ERM gives me the hypothesis H0. And what is the estimation error? Estimation error is the H0 compared to the best in class. So let's say I have risk of H0. I subtract the empirical risk of that hypothesis. I add the empirical risk minus the best in class. So the risk of this hypothesis minus the empirical risk is this term right here. This is obviously going to be, you know, this term is going to be less than the supremum over all h's, because H0 is just one possible item in capital H, right? If I replace it with the supremum of over every h, definitely this thing is less than that, right? And this is again the same thing. Why? Because empirical risk of H0 is less than the empirical risk of H star, because H0 is by definition something that minimizes the empirical risk. So risk of H star has to be greater than the risk of H0. So by going from here to here, I use the fact that H0 was an empirical risk minimizer, and going from here to here, I use the fact that both of these terms are independently going to be less than the absolute supremum. So the idea is that the risk of my empirical risk minimizer can be, its deviation from the best in class can be bounded by twice its deviation from its empirical error. So we don't really need to know what the best in class is. We can just look at this term and look at a factor of 2 and be able to say that, oh, the best in class can only be this far from it. It's pretty clever if you think about it. Because finding the best in class may not be easy, but finding the empirical risk, finding the H and its corresponding empirical risk is something that we can do. So how do we choose this hypothesis set H, right? That is the problem of the model selection, basically. And as you can see, this is the bias variance thing again. Let's say gamma is some sort of a complexity measure, so some sort of a complexity term, right? If you start increasing gamma, what you're going to see that the approximation error decreases a lot. And what was approximation error? Approximation error was the best in class to the Bayes error. Bayes error is 0, let's say. So as you keep increasing the complexity, you start putting in more and more and more and more functions, add neural networks, add LSTM, add transformers, add every possible model that you can. Surely the best in class can only go down, right? And that's what happens. Gamma goes down. Oh, sorry, the approximation error goes down. But the estimation error is increasing. Why? The estimation error is the difference between the risk versus the best in class. Now, if I have some data which is fixed, let's say, the estimation error increases. Why? Because as I increase gamma, my function space becomes so large that with that small amount of data, I cannot really hone in. I cannot really make really good comments about how good my chosen hypothesis is to the best in class, because the best in class is such an elusive target if you think about it. So the estimation error increases as you increase the gamma, and therefore there is a trade-off, the bias variance trade-off, which we talk about, you know. Anyway, another way to think about is the structural risk minimization thing. So what do you do is to find this particular, you know, best, like ideal choice of gamma, which is gamma star, like which gives the ideal trade-off between the complexity of the hypothesis set versus how hard it is to find the hypotheses within that, the complexity of finding the hypothesis set. Like there are two different things. So let's say gamma star gives us that ideal sweet spot. So how do we find this? So let's say we consider an infinite sequence of hypothesis sets, and all of them are like increasing, so to speak, in their complexity or whatever. So the structural risk minimization is, instead of just doing the empirical error minimization, you do the empirical error minimization, but then you also add a penalty for how complicated your hypothesis set is. So when Hn is higher, the penalty would be higher. Like the more complicated the more complicated hypotheses classes you use, the higher penalty you get. So the algorithm will try to choose simpler and simpler hypothesis sets. But then when you try to choose simpler and simpler hypothesis set, the empirical error may be too high. So you want to increase the complexity of the hypothesis set so that the argument is low, but then you want to reduce the complexity of the hypothesis set so that the penalty is low. So if I were to solve this computationally, I would achieve at a sweet spot, given how I define the penalty or whatever. So this has strong theoretical guarantees, but it is typically computationally hard, essentially. Because it is computationally hard. I think you can get the feel. Well, I can get the feel of the fact that how can this be computationally hard, because there are like sequences of sets, and within every set you have to find the argument and then calculate the penalty with that set, however we define it, but whatever. So this was just one way of trying to get at that bias variance trade-off. Empirical risk minimization is something that is just point blank empirical risk minimizer. Structural risk minimizer is do the empirical risk minimization, but also with a penalty. But then something that we also do is regularization. Like you do empirical risk minimization, but then you penalize for the norm of the hypothesis set you have selected. And this is something that is done in practice with the claim is that the norm of the function is some sort of a placeholder for this penalty variable. Because if the penalty increases, we would like to keep that norm low, but then we would also like to keep the argument low. So regularization is something that is actually used, and there is some sort of a feeling that this might actually be a placeholder for penalty. Like this has the same form of, if you look at it, these two equations look so similar. And it's indeed true. In some algorithms, regularization is kind of like structural minimization. We'll see. So now next part will be probability tools.